Welcome to our lesson today on functions. I hope you'll find that functions not only show up everywhere in math, but functions really show up everywhere in our world. Now, as our notes tell us here, a function is a one-to-one correspondence that basically takes one value from the domain, which we'll talk about here in just a moment, and it assigns that to one value in the range. And so let me just give you a little example. Let's take, for a domain, let's take the set of all people and assign there, for a range, we're going to look at birth dates, or birthdays, I guess. Alright, so for instance, my birthday is on April the 15th, so my birthday goes to April the 15th. If we look at somebody else's birthday, maybe Bob's birthday is March the 14th. That happens to be my granddad's birthday, and born on Pi Day for those of you that are interested, 3.14. But the point here is that each person has their own birthday. Now, many people may share the same birthday. For instance, I know I'm not the only person that was born on April the 15th, but that is the only day that I was born on. I don't have multiple birthdays. I only have one. Another example here, this would be one. Another example, for the domain, we could think about a car, and we could think about its vehicle identification number. Each car only has one vehicle identification number. Each car only has one license plate number. So these are all examples of functions. You take an input, it's assigned to one and only one output. If you're into sports, a baseball player, for example, only has one batting average at any given time. So these are examples of functions in everyday life. Now, when we think about functions in the mathematical world, if we think about the domain, and we think about the range. And so we have a function here, and this function will take a value from the domain, and it will, what we call, map it over here into a value in the range. Alright, so here's the domain of the function f. This is what goes into the function. What comes out of the function is f of x, and f of x lives in the range. We'll learn later, I'll mention it just briefly for now, we'll learn later that the inverse of this function, denoted like this, more to come on this later, but the inverse takes something from the range of f and sends it back to the domain of f. So this becomes the domain of f inverse, and this becomes the range of f inverse. Like I say, for now, what we're focused on are the domain and the range of the function. Domain of f and the range of f. Those are the two big things that we are looking at right now. Let's take a look here at this first example, and you'll notice that this is example 1 in our notes, problem 8f from the problem set. Now, if we think about how our function notation works here, notice it wants me to determine f of a plus h minus f of a all over h. Now, as I've mentioned before, I think I'm going to find what f of a plus h is first. Some teachers will have you do this all in one big shot. I'm going to find f of a plus h first. So this is 3 minus, now putting a plus h in anywhere there's an x, this becomes 3 minus the quantity a squared plus 2ah plus h squared, which is 3 minus a squared minus 2ah minus h squared. And then f of a, well, what is this? This is 3 minus a squared. So now that we've got these values identified, let's look over here. F of a plus h minus f of a all over h. Let's plug in. We know that f of a plus h looks like 3 minus a squared minus 2ah minus h squared minus f of a. I'm going to put this in parentheses, the quantity 3 minus a squared all over h. Now we'll simply simplify this. 3 minus a squared minus 2ah minus h squared minus 3 plus a squared all over h. Let's combine like terms here. Notice how those drop out, as do the a squareds. And so we're left with negative 2ah minus h squared all over h. We can factor an h out on top here, negative 2a minus h all over h. And this gives me negative 2a minus h. And so we have just determined the value of f of a plus h minus f of a all over h. We'll learn in calculus, for those of you going there, and I realize most of you are in one form or another, we'll learn that this is what we call the difference quotient. More on that later, just a little tease for now. If you would please, for class discussion, work problems 5 and 10, that would be wonderful. And then for homework, take a look at problems 6 and 9. Now, some very important results here, and we want to make sure we talk about these. The graph of a function f is the graph of the equation y equal f of x for x in the domain of f. So really what this is saying again, folks, is we've got my domain, we've got my range, and my function maps over to here. Here's my function f. We map from the domain over to the range, and then each of those points, if you think about it, we've got an x here, we've got an f of x here, and we're going to graph each of these x, f of x. Alright, we often attach the label y equal f of x to the sketch of the graph. If a point is a point on the graph, then the y-coordinate b is the function value f of a. And so really all they're saying here is if we've got a, then f of a is actually what they're calling a, b, the point a, b. Since there's exactly one value, f of a, for each input in the domain, there's only one point on the graph of f that has an x-coordinate of a. In general, we're going to use what we call the vertical line test to determine this. Every vertical line intersects the graph of a function in at most, this is really important, folks, in at most one point. Consequently, the graph of a function cannot be a figure, such as a circle, in which a vertical line may intersect the graph in more than one point. X-intercepts of the graph of the function f are solutions of the equation f of x equals 0. These numbers are called the zeros of the function. So really, when you look at a graph, the x-intercept of that function, or the x-intercepts, are the zeros. The y-intercept of the graph is f of 0 if it actually exists. They want us here to, in example 2, draw two graphs, the first which represents a function, the second which does not. So here's one that represents a function. Here we have this graph, and you see I can take any vertical line that I want, draw it through the graph, and it will intersect in at most one point. Let me give you another example here. Here's our friend the square root function, and if we draw a vertical line, any vertical line through this graph, we're supposed to change colors here. Any vertical line through any point in this graph, you'll notice that we have a function because the vertical lines intersect in at most one point. Now, not a function. We can take a look here. So here we go. Let's do something that's not a function. There's an example of if I take a vertical line and draw it through, if it crosses anywhere in more than one spot, we do not have a function. We do not have a function. All right, I'll give you another example of something that's not a function. If we have something like this, we can see that we can take a red vertical line and we can draw it through here, and it will cross in more than one spot. So here's an example of how we can use the vertical line test. So let's put together some of the facts that we know about functions at this point. We know that the domain is a set of all x values that get hit. If we look at this graph, we always look at domain, we look from left to right. Notice starting here at x equal -4 and going over to x equal -2, those x values are all included in the domain of the function, as are the x values from well, actually, the -2 continues on. Look, -2's in there. Everything to the right of -2 goes on until we get to 4. Now, 4 is not included. So let's fix this here. We had two pieces. Kind of fooled me. We got to watch out for this. But we're looking to see what x values are hit. And we see that all the x values starting at -4 and running all the way over here to +4 are included. Now you'll notice +4, there's an open dot there, and so this is our domain. Now the range, well, first of all, let me say when we think about domain, we're thinking left to right because we're looking at the x values. When we think about the range, we're looking bottoms up. In other words, we're looking for the lowest y value that's hit all the way up to the highest y value that's hit. And if we look at this, we see that -3, okay, is that's where it starts. Now we can't include -3, but we go up to, but we don't include -1. And then starting again at y equal 1 and going up to y equal 3. Now notice here these are closed dots, so we are going to include those endpoints. And those are the values in the range of this particular graph. Notice part C wants me to find f of 1. And so you'll remember what this means is we want the y value when x is 1. Well, let's take a look over here. When x is 1, we slide down here. And admittedly on this, we have to estimate just a bit, but we're going to call this -1. When x is 1, f of 1 is -1. So when x equal 1, y equal -1. And here if we look at part D, D says find all x such that f of x equals 1. Well, let's look at this, folks. Here's y equal 1. The only x value it looks like that causes y to equal 1 is x equal -2. And then if we look at part E, we're looking for all x's such that f of x is bigger than 1. The y values, in other words, are bigger than 1, and we can see that right in this little region. Now remember, when we write an interval, we always write the smallest number first. So we're going to start with -4. And we're going to go over here to, where are we at? Over here looks like to -2. Now remember, we can't include -2 here because at -2 we have determined that the y value is exactly 1, not greater than 1. So all x's, what did we find here? All x values for which y is greater than 1. And now there are no problems to work here for our class discussion. Just look at 17, 19, and 20. And of course, if you have questions on those, please bring those up in class, and we'll be happy to go over those. Now, so far, most of the functions we've studied have had a domain that was a set of all real numbers. We have talked about rational functions. We've got to be a little bit careful here. Rational function, the ratio of a polynomial p to the polynomial of q. We've got to make sure that q of x is not the zero polynomial. The other thing that we've looked at, if we've got g of x equal to the square root of f of x, we have to make sure that f of x is greater than or equal to 0. Other than that, to this point, we really haven't had to worry too much about what the domain is going to be. We'll study some examples here, or study some functions rather, coming up in this class where we will have to pay some attention to what the domain is. But for now, those are the two biggies. And of course, both of those would rear their ugly heads for us in this next example. So let's take a look here at example 4 in our notes, which is problem 27 in your problem set. First thing we need to do, or it really doesn't matter here what order we go, but we know that 2x minus 5 needs to be greater than or equal to 0. Well, this means 2x needs to be greater than or equal to 5, and x needs to be greater than or equal to 5 halves. Now, at the same time, we need to know where x squared minus 5x plus 4 equals 0. Well, let's see. X minus 1, x minus 4. This equals 0. We know that when x is 1 and when x is 4, our denominator is going to be 0, which is no good. Well, let's see. Let's take a little gander here. We know that x has to be greater than or equal to 5 halves. So it's got to be somewhere in here on the number line. Now 1 is over here. That's not a problem, but we know that 5 halves is 2.5, and here's 4. Well, we said that x can't be 4. So when we get ready to write our domain here, guys, there's a couple different ways we could do this. We could use one of my favorite notations, what we call set builder notation. This is a set of all x such that x is greater than or equal to 5 halves and x can't be 4. Or some notation that you may be more comfortable with. We'll give you the choice. I don't really care which way we go here. We can go with all reals from 5 halves to 4, parenthesis on 4 now because we can't include it, and then again from 4 to infinity. So either way, we can represent what the domain of this particular function is, and we've got to be careful to make sure that we don't have a negative under a radical, or that we can't have 0 in the denominator. All right, and so along those lines, please take a look at problems 24 and 28 for class discussion. You can see the homework there that I'll be potentially checking 21, 3, 5, 6, 9, and 32. And now we're going to talk about some more characteristics of functions. I think that these definitions really don't need to be as hard as what this notation might make them out to be. Basically, folks, a function is increasing if we get on this thing and we ride this going from left to right. If we're going uphill, we have an increasing function. If we're going downhill, here we are on roller skates, our little guy on the bicycle, you can see why I'm not an art major. He's having a good time, If we look at this from left to right and we're going downhill, we are decreasing. Folks, you read a book from left to right, and that's the way you look at a graph. Now, if you look here and you're walking along and life is good, walking along, little stick figure here on this flat surface, then we have a constant function. Let's take a look now. It basically says if f of x1 is less than f of x2, whenever x1 is less than x2, then it's increasing. So as my x's get bigger, my y's get bigger. Here on a decreasing function, my x's are getting bigger, my y's are getting smaller. And on my constant function, as my x's stay the same, so do my y's. And of course, if we're going to talk about this, well, we need to look at an example here. And so we might know that, we're going to have a graph that's got a little bit of everything in it. Now remember, the domain just talks about what x values we're going to hit here. And when we look, we always list the domain from left to right. Notice we start at -5 and we go over to -3. Now we're not including -3 because there's an open hole here. And then we pick up -2. We don't include it because, again, an open hole. And we go to -1, closed circle right there. And then the x values go from 0 to 2. Now we get to include 0 because there's a closed circle, but we can't include 2 because there's an open circle. And then check this out, folks. My x values starting at just a little bit bigger than 3 go all the way over to 5. So we can't include 3, but we do get to include 5, and that's my domain. Now, let's think about the range here. The range is a set of all y values. Now, folks, this may be a little trickier. We need to think about the y values that get hit. Remember, I asked you to look bottoms up when we talk about the range. Now, we can see that from -3 up to 3 were included. Now, you say, well, that's an open hole there. We can't include 3. That is true, but if we look over here, we've got a closed hole. And so 3 does get to be included. And then it looks like for a while here, y equal 4 is included. So let's see, we need to be a little careful how we write this. We start at -3, and we get to go up to +3. So there's that interval, and then the other y value that's included is y equal 4. Now we get to talk about where this function is increasing. Well, let's see. Now remember, folks, increasing, decreasing, and constant, we're thinking about x values. All right, x values here. So for instance, we're going uphill from x equal -5 to -3. We are also going uphill over here from 3 to 4. Now, where are we going downhill? Where are we decreasing? And again, folks, this answer is going to involve the x values here. We are decreasing from 0 down to 2, and that appears to be the only spot. And then where are we constant? Well, this graph has a horizontal line from -2 over to -1. And then again from 3, we're constant, looks like from 4 to 5. So we're constant from 4 to 5. All right. And so now for class discussion, work problems 38 through 42. And certainly if you have questions on those or on 33 through 35 or 37, 39, 40, we'll take a look at those when we get into class. Well, let's take a look at this bad boy. We're kind of putting together everything that we've just talked about here over the last few lessons, really. We've got a difference quotient here, and that we're asked to simplify. And so we've got f of x already. We'll note what f of a is. F of a is the square root of a minus 3. And so f of x minus f of a all over x minus a. Let's see what we have here. This is the square root of x minus 3 minus the square root of a minus 3 all over x minus a. And you say, well, how do we go about simplifying this? Well, our little hint says let's rationalize the numerator. And so the conjugate of our numerator here is the square root of x minus 3 plus the square root of a plus 3. And we know whatever we multiply the top by, we must multiply the bottom by as well. One of our 10 commandments of algebra, whatsoever you multiply the top by, multiply the bottom by as well. And we know how it works when you multiply two conjugates together. You take the square of the first term and subtract the square of the back term. And this is all going to be over my bottom, which is x minus a, times the square root of x minus 3, plus the square root of a. Whoa here, folks. We have a correction that needs to be made, not a plus 3. We need a minus 3 there. That would have caused a little confusion. So we'll make that correction. Maybe. There we go. And a minus 3 right there. Alright, so when we square a square root, we get our radicand, x minus a minus parentheses, a minus 3, x minus 3, there we go. And this is all over x minus a times the square root of x minus 3 minus the square root of a minus 3. Alright, and let's come on up here. We'll have a little more room. So on top, folks, we're left with x minus 3 minus a plus 3 all over x minus a times the square root of x minus 3 minus the square root of a minus 3. And so what do we get? Well, the 3's drop out. We're left with x minus a over the quantity x minus a times x minus 3 minus the square root of a minus 3. Well, let's check this out, guys. Notice the x minus a's cancel, and we're left with 1 over the square root of x minus 3 minus the square root of a minus 3. And I really don't need my parentheses there. I'll go ahead and take them out. There we have it. Wasn't that exciting? So we've just simplified the difference quotient there, and we got the opportunity to remember what it was like to rationalize. Pretty cool, huh? Got a lot of bang for our buck in that example. And so now for the class discussion, if you'd look at problem 49, I would appreciate that. So would your grade. And for homework, we'll look at problems 47 and 50. Alrighty. Well, wouldn't be a good set of lecture notes if we didn't have a word problem in here to kind of tie some of this together. And if you look in your textbook, you'll see the diagram for this. When you look in your notes that you get to print out from Angel, you'll see that I thought to include the diagram. However, since I forgot to include the diagram here in these notes, let me give you a quick sketch of what we're looking at here. We got a 3-foot door there, and we've got a 3-foot doorway here. We are told that this distance is going to be y, this distance is going to be x. And so now that we've got our diagram in place, and we all know that I'm not an artist, so it's not going to matter. It says a small office unit is to contain 500 square feet of floor space. A simplified model is shown in the figure that I just drew. We want to express the length y as a function of the width x. Well, let's see here. We know that for part A, we know that x times y, my area, equals 500. And so y is a function of x. This is going to be 500 over x. And now it says if the walls cost $100 per running foot, express the cost C of the walls as a function of the width x, disregarding the wall space above the doors and the thickness of the walls. Basically, what we're after here is the total perimeter, basically. So total perimeter. Now let's first define this in terms of x and y, and then once we get that done, we'll pull the y's out. You see, for the perimeter here, you'll notice that this length is x minus 3, and you'll notice here that this length is also x minus 3. Alright, so when we look at this total perimeter, we've got 2y plus 2 times x minus 3, and then we need to add in an x. Alright, so this gives me my total perimeter. Now we'll keep in mind that we are going to substitute 500 over x in for y. Okay, and I'll leave this as 2 times the quantity x minus 3 plus x. So what do we have here? Well, we've got 1,000 over x plus 2x minus 6 plus x. Let's clean this up now. We have 3x plus 1,000 over x minus 6. That equals my perimeter in terms of x. And for our cost function here, we know that it costs $100 per running foot. So my cost is equal to 100 times 3x plus 1,000x minus 6. And we can multiply this out so that we get 300x plus 100,000 over x minus 600. And there's our cost. And so if you would kindly look at problem 69 for class discussion, 68 can go in your homework. And that will conclude our discussion today on functions.